So we skipped lesson 3. Actually, I combined lessons 1, 2, and 3 into 2 lessons to try and save one whole day. So we've talked about electric force, Coulombs Law, like charges repel, unlike charges attract. We've said what causes or what spreads, what transmits that force. We talked about action at a distance. Was witchcraft not allowed? We said actually no, charges are touching each other. It's just invisible. They're touching each other with electric fields. Well, what we want to talk about today then is energy. Let's suppose in my hand I was holding something that was charged positively, really, really positively charged. And over here I have an electron. What's the electron going to want to do? It's going to want to fall towards the big planet. And I'm putting it in gravitational terms now, even though that's not quite right. Okay? If it falls, it must have potential energy. In fact, that potential energy turns into kinetic. Or, what if this was a huge negative charge and I had an electron right here? What does this electron want to do? Okay, now it wants to fly up, fall away, repel. But it also has potential energy. But in this case, its potential energy would send it out to infinity. It depends on whether our charges are the same polarity or different. But definitely, they must possess some type of potential energy if they would fall or move if you let them go. Is that okay, Sammy? So we're going to define electric potential energy, PE, in a manner similar to orbital gravitational potential energy. We say that electric potential energy reflects the work that must be done to move a negative charge, little q, near a positive charge, big Q, out to infinity. So if this is negative and this is positive, little q wants to move to the left. That means we would have to do work. We would have to lift it to get it to move to the right, and we would feel it straining against us, wanting to fall back down to the left, which means we would do work. The same way as rocket fuel has to do work to lift a rocket from planet Earth. Or, if we had identical charges, if this was negative, and we started out very far away, it would be how much work it took to push it closer, because it didn't want to get closer, it's repelling, how much work it took to push it closer. So we can either think of it as how much work to move a charge out to infinity, or how much work to move from infinity out to a relatively close distance, depending on whether the signs are the same or opposite. Recall, we said the force between two charges is not constant, varies with distance. This is Coulombs Law. And as well with the varying force, we can't use force times distance because the force is changing. It's really the area underneath the force versus distance graph. You know what? I'm going to go straight to the punchline. Electric potential energy between 2 point charges, 2 circular charges. By the way, doesn't this look an awful lot like big G, big M, little m over R? Oh, negative. Why not negative here? Because things can fly up or fly down. In fact, we're going to have to just, the equation looks very similar. It's force, but instead of a squared on the bottom, you have just an R. The same way as energy for gravitation was force, but instead of a squared on the bottom, you had just an R. Oh, and you also had a negative with energy. So I hope, Curtis, you noticed they look very similar, yes? Okay. How are we going to determine whether you're losing energy or gaining energy? Well, here's what we're going to say. For potential energy, here we are going to include positives and negatives. Unlike for forces and fields where we forget the signs, forces and fields in the first row of your formula sheet. We forget the signs, all those F's there. For work and energy, we're going to include the plus and minus. And if we get a negative answer, what that means is the object is losing energy. It wants to fall that way. If we get a positive answer, what that means is we would have to, it doesn't want to go that way, we would have to add energy, we would have to do work to get it to move to that location. Remember, scalars include signs. Energy is a scalar, and you better put the sign, the positive or negative sign in. By this relationship, just like for gravity, potential energy is 0 out of infinity. Oh, but by this relationship, unlike charges, have a negative potential energy, just like masses had negative potential energy, because we had the negative potential energy, Alex, when the small mass wanted to fall towards the big mass. With unlike charges, the small charge wants to fall towards the big charge. It takes work to separate them. Example 1. Find the potential energy of a negative 75 microcoulomb charge that's 3 centimeters away from a positive 120 microcoulomb charge. Okay, let's do that first. I think I can do that. How much, did I give you guys a whole page? Oh, I did. Okay, then I don't need to fit A up there, I don't think. Potential energy, electric potential energy, is equal to K Q1 Q2 over R, which is going to be 9 times 10 to the 9th charge 1. Which is the one that's standing still? Look at the picture. Which is the one that's not moving? I always let the one that's not moving be charge 1, just so my work all looks the same. So I'm going to say 120 microcoulombs. Charge 2, negative 75 microcoulombs all over. We're starting out 0.03 meters. How much potential energy does charge 2 have at that location? I get negative 2,700 joules. Double check me, yes, no? Why negative? Because where do we define 0? Out at infinity. Would you have to do work? Would you have to add energy to get it out to infinity? Yeah, because it wants to move towards that 120. You'd have to be pulling and pulling and pulling and pulling to get it to go to the right. You would have to add energy to get to 0. Yep. Not if it's all the way out at infinity. Then it has no. Then you've removed it from the electric field, and it won't want to fall anymore. The same way as a satellite out at infinity can just float there without being in orbit, right? Is that okay? Yeah. B. Write a work energy equation. Okay. Work equals the change in potential plus the change in kinetic. You'll notice I skipped, Elijah, force times distance, because I know the force isn't constant. Actually, the further I move away, the weaker the force, so I can't use force times distance. Also, I think we're going to assume start and end at rest. Start and end at rest. So this is going to be PE out at infinity, final, minus PE initial. You okay with that 8 on its side? That's the symbol for infinity. But Nate, what did we just say? What is the potential energy out at infinity? We've defined it as 0 minus, and what did we say our initial potential energy was? Negative. And I think now this sort of answers your question. You can see, oh, I would have to do positive work to get it out to infinity. The signs take care of themselves that way, based on how we defined 0 relative to 0 to infinity. By the way, the alternate would be, what if it fell from infinity down towards the ground? That would also be a change in potential plus a change in kinetic. But there I would probably say, hey, is there a change in height? Is there a change in speed? If you want me to find V final, I would use conservation of energy. Kinetic initial, potential initial equals kinetic final, potential final. C. Find the work done by the applied force. Oh. I guess B only wanted the equation. C said, you know what? You would have to do 2,700 joules of work to move that second negative 75 microcoulomb charge completely from the electric field of that 125 microcoulomb charge. 120 microcoulomb charge. Turn the page. Kelly, by this equation, by this relationship, like charges have positive potential energy. This makes sense because it takes work to overcome the electrical repulsion and push the charges together. So example 2 says, find the work required for an external agent. Folks, when I say external agent, you can envision little invisible angels. And I'm not being facetious. I'm saying something off of the screen, leprechauns, angels, something is adding energy to the system, but I don't want it to have its own electric field. I don't want it to have its own mass. I don't want it to have its gravitational field. So I'll go to mythical creatures, unicorns, angels, leprechauns, whatever you want to put there. Tall point guards. Mythical creatures? Okay, sorry. Okay, take a look at this picture here. Hakeem, can you see this positive charge doesn't want to move towards this positive charge? We're going to hold this one in place. Let's imagine it's thumbtacked to the ground or something like that. So for us to bring this in, the closer we get, the more it's going to push against us, the more it's going to repel, the more work this external agent is going to have to do. What did this question want me to find, Alex? Can I use force times distance? Because the force is not constant. You know what? Work is going to be Is this question mentioning a change in speed at all, though, Alex? Say no. And what's changing anything? Where am I initially? What does the diagram say? So how much potential energy do I have out there? Nice. Right? Relative to 0 at infinity. So you know what? How much work it's going to take is how much potential energy I end up with, which is going to be K Q1 Q2 over R. And again, we're doing energy, we're doing a scalar. We're going to put the positives and negatives in. Now in this case, they're both positive, but can you see, hard joke, this would also work if they were both negative, because they were both negative, I'd have a negative times a negative, which is still I get a positive answer, and if they're both negative, they would still be repelling each other. It's the same idea, okay? So it's going to be 9 times 10 to the 9th. The fixed charge, 1.75. Claire, what's that lowercase m in front of the C stand for? Is that micro? Sorry? No, micro is that symbol there. There's not a micro symbol. This is milli, which is 10 to the negative what? Good, Claire. You are ever so smart. 2.5 times 10 to the negative 3 all over R final, which is 5 meters. How much work would this take? How much work would that take? Oh, by the way, Petra, common mistakes. Kids square the R because they're so used to doing it. For electric field, it was R squared, and for forces, it was R squared. But I think I did my formula sheet rant last class where I said you want your formula sheet in front of you during this unit because you can train your eyes to look in the right location, because all 4 major equations look really, 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 really similar. And I also said something like you want to practice these on your calculator, right? Do you get 78, 75? To 3 sig figs, 78, 80 joules of work. So Nate, going back to your question, I hope I've convinced you. Actually, the signs and everything take care of it. We can still use our old definition, and as long as we put the positive and negatives in, we get answers that we expect. Is that okay? So for energy, a scalar, we will include the plus or minus, unlike forces and fields where we will forget the sign. Okay? Forces and fields, we decided the direction. For forces, it was which way would for forces it was like repel, unlike attract. For electric field, it was which way would a positive want to move it could. Here, we include the signs. Oh, and then I wrote, if there is no external agent, no unicorn, no invisible angels pushing the charges around, then the energy of the system will be conserved. I can use the law of conservation of energy. Example 3. An electron is originally that far from a proton, and at rest it is released. You know what? If you release it, it's going to fall towards the proton. The same way as if you dropped something. Find its speed when it's that far from the proton. Is there a change in height? Yeah, it's sideways, but yeah. Is there a change in speed? Yeah. Are there non-constant forces? That's also a job for conservation of energy. But make sure for PE final, I'm not using MGH. I'm using electric potential energy, because that's behaving like gravity. Are any of these 0? Sorry? Starting at rest. Are we starting out at infinity? Nope. Are we ending at infinity? Nope. Are we ending at rest? No. What's this question want me to find, Cliff? Which is, I think, going to be in the KE final. I get the KE final by itself first. I think I'm going to have this. Initial potential, take away, final potential equals KE final. I think I'm going to have K Q1 Q2 over R initial minus K Q1 Q2 over R final. Kind of a negative change in, because if change in is final minus initial, here I have initial minus final, but that's okay. That equals a half mv final squared. You know what? I could get the v by itself, but I think Callum, it's going to be ugly. I think what I'm going to do is I'm actually going to crunch the left-hand side, get an answer to like 5 sig figs, and then I'll go times by 2, divide by mass square root. Is that okay? So K? 9 times 10 to the ninth. Charge 1. It's a proton. Okay, positive. More specific, it's a proton. 1.6 times 10 to the negative 19. Charge 2, it's an electron. Negative 1.6 times 10 to the negative 19. All over our initial 2.5 times 10 to the negative 11. Minus, what's K? 9 times 10 to the 9. What's charge 1? Proton. What's charge 2? I'm going to use the same cheap trick that I did in the gravity. I'm going to go ditto mark, ditto mark, ditto mark, all over. What's our final? That equals a half mv final squared. Nine times 10 to the ninth. 1.6 times 10 to the negative 19. Negative 1.6 times 10 to the negative 19. Divided by 2.5 times 10 to the negative 11. 11. Positive times negative, yep. I get negative 9.216 times 10 to the negative 18. Take away. All the same numbers on the top, just change the bottom to 1.0. Negative 2.304 times 10 to the negative 17. That equals a half mv final squared. I got room? Good. Negative 9.216 times 10 to the negative 19 divided by Mr. Dueck, minus that answer. Whew, I was hoping to get a positive answer. 1.3824 times 10 to the negative 17. 1.3824. 1.3824. And apparently that equals a half mv final squared. How would I get the v by itself? Oh, I like this question. I like this question. I like this question. I like this question. How do I get the v by itself? Really? How do I get the v by itself? Times by 2? Divided by m. Which m? What's moving? Okay. So this is going to be times by 2 divide by the mass of an electron. Which mass? It's an electron. It's on your formula sheet somewhere, I think. I think this is 9 point, it's 9.11, but I can't remember the rest. 10 to the? I just drew an arrow pointing down there because I didn't feel like rewriting all this. So, 2 times that divided by 9.11, negative 31, square root. Woo! We're moving pretty fast. 5.5 times 10 to the 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Who knows what the speed of light is? 3 times 10 to the what?
8.
By the way, it couldn't be 3 times 10 to the 6th because this would be violating Einstein's law of relativity because it's moving faster. Yeah, 3 times 10 to the 8th. So we're going about 100 times slower than light. Closer to 50 times slower than light, but still, we're moving pretty good. Turn the page. Last one. Psst. Shh. Sammy, what's this asking me to find?
How much potential energy has the negative 1 microcoulomb charge plus?
Good save. The negative 1 mu. No, it's not mu. The micro. Yeah. Watch and learn. Okay. Now, I would have no problem giving you this diagram and say, hey, find the net force on the negative 1 charge. That would require Pythagoras and trig. I would have no problem removing that negative 1 and just putting an X right there and saying, find the net electric field right there. That would require doing electric field twice, adding together tip to tail, and doing some trig. But here's the beauty. Energy, scalar or vector. I'm going to find the potential energy between those two, the potential energy between those two, and I don't care what angle they're at, I'm just going to add them up. So even if this was at a yucky angle with that charge right there, and you'd be saying, well, don't I have to use the cosine? Actually, no, work and energy is a lovely scalar. In fact, one of the classic ones that they'll give, one of the classic diagrams that they'll give you is they'll give you a charge here, and they'll say, if you start out in that location and you end up in that location, what's your change in potential energy? And they'll give you these distances, but they won't give you any of the angles, and kids are freaking, go, ah! It's a scalar. Find how much energy there, find how much energy there. The change in is final minus initial. Who cares? No angles, no trig, no nothing. So I'm going to call this charge 1. Also conveniently, charge 1 has a magnitude of 1. So I'm going to choose to call this charge 2. Why? Because also conveniently, charge 2 has a magnitude of 2. I figured that'll help me keep from getting them mixed up. Okay, charge 3 is going to be the 5, but I'm trying, any trick I can do, Jacob, to avoid making a mistake, I'll do. So what I'm going to do then is I'm going to find the PE between charge 1 and 3. I'm going to find the potential energy between charge 1 and 2. And then no trig, no tip to tail. Going to add them up. K Q1 Q3 over the radius between 1 and 3. I'll call that R13, 1 and 3. Oh, and this one's going to be K Q1 Q2 over the radius between 1 and 2. Honestly, now it's plug and chug, Alex. Complicated, absolutely plug and chug, scientific notation, but plug and chug. What's K? It's on your formula sheet, Alex. What's K? It's a nice constant. Yeah, it's a nice one. Most kids memorize that one because, it's a 9 and a 9, right? So 9 times 10 to the 9th. Alex, my friend, what's charge 1? Include the negative 1 microcoulomb. What's charge 2? Include the negative 2 microcoulombs. Alex, what's the distance between them? Careful, don't say 4. Sorry, what? Oh, I'm doing 1 and 3. Sorry. Which is positive 5 Microcoulombs. Sorry, you're right. I did 1 and 3. I don't know why I did 1 and 3, because I guess, I don't know. Alex, what's the distance between 1 and 3? Don't say 2. Careful. Trap the units. Did you say, 0.02? Without the dramatic pause, it would have been a little more effective. I liked, raising the drama. That was very nice. Shakespeare would be proud, right? 0.02. Or not 0.02. That is the, okay. Anyways, so 0.02 squared? No, not for energy. And I'm going to try and emphasize where kids zig. And the number of times I'll see a squared down here drives me crazy. Because unfortunately, I have to assume that you meant to find the force, and I got to give you 0. How much potential energy does charge 1 is there between charge 1 and charge 3? You're going to get a negative answer, I can tell you that. Negative 2.25 joules? Yeah. Okay. By the way, what that also means is if you wanted to move charge 1 out to infinity, you'd have to add energy because it wants to move towards charge 3. That's what that negative means. Okay, let's find the potential energy between charge 1 and 2. 9 times 10, wow, that's terrible, times 10 to the 9th. Include the sign. Include the sign. And Alex, do the dramatic pause again. What's the distance between charge 1 and 2? Don't say 4.
0.04.
Oh, I like that. Leaves you hanging and then brings it home. That's very William Shatner-ish, right? I don't know what to do next, right? Yeah, very good. 0.04. You're going to get a positive amount of energy between those two because you have a negative times a negative. Again, what that's saying is you would have to do work to move them closer because they don't want to be closer. What do you get? 0.45? And here's the beauty. Energy is a scalar, so P, E, total. No trig, no need angle, no direction. It's going to be negative 2.25 plus 0.45. You know what? I can even do that in my head. I think the charge has negative 1 point. Dramatic pause. Negative 1.85, is that right? Or 7.5? No. Negative 1.8. Is that right? Negative 1.8 even? What that says is in this charge configuration, if you thumbtacked the corner charges to this piece of paper, would you have to do work to move it to infinity, or would it want to move here from infinity? Did we get a negative energy or a positive energy when we did the net energy? Negative. That means it doesn't want to leave this location. You would have to pull to bring it out to infinity. If we'd gotten a positive answer, it'd be saying, you know what? If you wanted to bring that charge into that location, you'd have to push and add energy. Is that okay? What's your homework? Wow. Sure, I'll say try number 1. Number 1, skip C. The only reason I'm skipping C is I don't know which charge they want me to find the energy on. I think maybe it's the 1, but I'm not sure. Unless they want me to find the energy between all 3 and add them up, and that's the energy of that system. But I'm going to 2, absolutely. 3, I like number 3, I like number 3, I like number 3. Skip 4. 5. There's a small typo in number. Did I fix it on yours? Does yours say final on number 5 right there? Okay. Because initial is far away, final is in close. Six. Now, number 8. Number 8. A is fair game. B is nastier than I'll ask you. It wants you to find the electric field at point X, but there's 3 charges to deal. In other words, you'll have to find the electric field from charge 1, magnitude and direction at that location. Electric field from charge 2, magnitude and direction at that location. Electric field from charge 3, magnitude and direction at that location, and then add them vectorially. 3 charges is overkill. It's fair game for homework, but I'm telling you on your test, if I say find the electric field and it's a multiple charge situation, I'm going to cap it at 2 charges, and I'm going to say, oh, for Pete's sakes, if you could find it between 2 charges, you could find it between 8 charges if I felt like being that way. So I'm going to assign 8 for homework, but just letting you know, little overkill. 8A is okay. I have no problem asking you to find the force on 1 charge from 2 other charges. No problem there. Okay? Oh, heck. Let's do some conservation of energy. Let's do 9 and 10. Some conservation of energy review and some winner minus loser Atwood machine review.